Just see. Okay. Welcome, people. Good evening, morning, day from to the whole of the world from BH Futures Foundation. Welcome to the seventh webinar. My name is Alma Beciragic, and I'm coordinator of Makerspace Network in BH Futures Foundation. And tonight I have an honor to be your host. In tonight's webinar, we are hosting Alma Beciragic. To be furthermore known by the topic of this webinar, it's great knowledge that to know about the what's whole world talking about. So, UN Agenda 2030 has set goal 6 in UN Sustainable Development Goals, which is considered to be a goal of clean water sources. Alma Beciragic was awarded by the Queen's University of Charlotte Presidential Scholarship, where she studied environmental science and chemistry and participated in several research projects on federal and local levels. In August 2014, Alma began her doctoral studies at UN Chapel Hill as a part of Environmental Science and Engineering Department in Gilling's School of Global Public Health. Her research explores questions relating to reverse osmosis and nanofiltration, membrane leaches by byproduct formations as a result of membrane disinfectant interactions. So, if you haven't watched the video as a call for this webinar, it's your pity because it's a really great video and I'm really honored to host Alma. So I'm letting her the word. Thank you, Alma, for being here tonight with us and taking time to teach us something more about the leaching from the membrane.
Okay. Hi, everyone. Can you hear me?
Yeah.
Okay. Should I turn the camera on now? Okay. Hi, everyone. My name is Alma Beciragic. I am a student at the Gilling School of Global Public Health at UNC Chapel Hill. And today I hope to kind of spark your interest about a passion of mine, a really neat technology, membranes and membranes for water treatment specifically. So with that, I'll start. A little bit about me. So I did my undergraduate work at UNC, or Queen's University of Charlotte, and during my time there, I had the pleasure of working with several organizations, National Oceanic and Atmospheric Administration, where I worked with remote sensing to map the national shoreline. I worked with the Environmental Research and Education Foundation, where it was like a solid waste management kind of project. But what really struck my interest was my work with Charlotte Water in UNC Charlotte, and that was my first kind of portal into the world of water treatment and what kind of intricacies are associated with water treatment, and just the kind of the knowledge that's often taken for granted when you turn on your tap and there's just clean water there. So with that newfound passion, I went to UNC Chapel Hill to pursue I'm still working on my PhD in analytical chemistry and water treatment, particularly with membranes. So that's something we'll talk about in this webinar, and I hope that I can convey and then that by the end of it you think they're as cool and as powerful as I do. Throughout my time here, so far I've been in contact with several organizations that are now affiliated with my research, some of which are listed here: American Water, the American Membrane Technology Association, American Waterworks Association, Arcadis. So all of these organizations have somehow supported this research and also offer, if I may add, really neat student opportunities for conferences or presentations or mentorship. So that was huge proponent of joining those if you can. So to begin with the webinar, if you had a chance to watch the little promo video, I talked about day 0. So in January of 2018, Cape Town announced that the city of 4 million people was 3 months away from running out of municipal water. And you can see some of the headlines there from that time. Cape Town drought declared national disaster. And day 0 was the day that it was scheduled that the city would run. So luckily, Cape Town was able to avert this crisis. And part of the solution was obviously conservation efforts, but in addition to that, building desalination plants. Desalination plants are able to utilize seawater and produce drinking water from that. So as an outline for my presentation, first I will talk about membranes for water treatment and introduce a little bit of background. So water scarcity, the role of reuse, and define a couple terms that will become useful later on. Excuse me. Secondary effluent, natural organic matter, disinfection byproducts, and desalination. We'll talk about membrane types. We'll talk about the structure and active layer synthesis. And then I will go into a couple challenges relevant to the technology. So the challenge that my work focuses on for the most part are these leachates and byproducts. So there are kind of unknowns that are coming from these membrane materials, and my research group here is working to identify what those are and hopefully quantify some of those. I'll also talk about biofouling. That's another major challenge that membranes, however powerful and effective they may be at removing some of these contaminants that we'll talk about later, they are susceptible to something called biofouling, which is the accumulation of microbes on the surface. When that happens, their performance kind of degrades over time. And finally, I will conclude the webinar with a couple of recent advances and research directions, some that I thought were really, really neat, not necessarily related to my research, my current research particularly, but just some that I wanted to highlight to hopefully spark your curiosity into membranes. So it's estimated that about 700 million people worldwide currently live in water scarce regions, and by 2030, almost half of the world's population will be living in areas of high stress. Right now, you can see on the map on the right side, kind of domestic water usage in gallons per day per person across the United States, and how that varies. So on average, water usage per day is about 100 gallons per person in the United States. And with this kind of rising demand for water, there is a push for finding alternative sources of water and alternative treatment options to augment current water supplies. So that's where membranes come in, and because the demand for potable water or drinkable water exceeds its availability from natural sources right now, membranes are able to guide us into these two options that I'll be discussing: desalination and advanced water treatment. And these two options allow us to take advantage of water sources that can help augment or complement the existing water supply. So for desalination, I'll talk about desalination first. That is the ability to take seawater and reject salts in order to make it drinkable water. And the second one is the advanced water treatment for potable reuse applications. It's the treatment of secondary effluent. So in order to understand the advanced water treatment, we're going to walk through conventional water treatment first, conventional wastewater treatment, and then kind of map together where membranes fall in that scheme of advanced water treatment. So I will be in the following slides showing you quite a few kind of schematics of treatment scenarios, water treatment trains. And what I hope, the kind of main idea of that is just to get an idea of the steps relevant to treatment and where membranes fall within that sequence. So the first treatment train we'll talk about is desalination, and you can see here the seawater enters, and it's usually disinfected, and a coagulant is added, and it goes through a multimedia filter. This will help remove suspended particles, for instance. It goes into a filtrate tank, after which you notice that there's dechlorination, the addition of an antiscalant, and a biocide. So these three these three additions really help protect the membrane modules, which you see here. So dechlorination is important because chlorine, and we'll talk about this later, chlorine has the ability to react with the membrane surface and cause damage. And when those membrane surfaces are damaged, they don't reject contaminants as well. So very critical to have a dechlorination step here. Antiscalant and biocide help with making sure that the surface of that membrane is not covered in, for instance, the microbes to fight against biofouling. So then here are the RO modules that the water would be going into, and the product water or the finished water or clean water would be exiting here, and it would be going to be disinfected subsequently. And the brine, or the concentrated wastewater at that point, the super salty water, can recirculate through that system again. So the second treatment kind of train that we'll talk about, so the desalination was the first one where membranes are important, and then advanced water treatment was the second one that we'll talk about. But as I mentioned before, in order to understand advanced water treatment, we need to walk through conventional approaches to water treatment. So here is a kind of big picture schematic of what the sequence would look like. So the water would go through the drinking water treatment plant, it would go to your home. Consumers would use this water, it would be sent to a conventional wastewater treatment plant, and after it's treated there, go back into an environmental buffer, and the cycle starts again. So to begin understanding what is behind the drinking water treatment plant and the conventional wastewater treatment plant, we'll show you two more schematics. And again, the main purpose of these schematics is not necessarily to memorize, to understand every single step, just to understand the sequence of steps relevant for each. So for drinking water treatment, we have the influent from the surface water or the environmental buffer. This can be a lake, for instance, and there's a screen to remove larger materials. There is an oxidant or disinfectant added, a coagulant, and these are very kind of standard steps in water treatment. So coagulation, flocculation, sedimentation, filtration, and then clear water storage here. And that just means once the water has gone through all of these steps to remove, each removing a different type of contaminant, it's sent to the clear well storage and then eventually to the distribution system. So kind of an interesting fact here is that water, when you add this disinfectant here, sometimes in some cities, depending on the size of the city, water will have to travel for up to 15 days, if not more, before it reaches your home. So that means that residual needs to be high enough to last 15 days until it reaches the tap in your home. So coming back to the big picture, so now that we understand drinking water treatment and the sequence there, let's go over to conventional wastewater treatment. So once you've used the water that's delivered to your home, what happens to it then? So the top here is just a very simplified kind of sequence of the treatment steps. So again, preliminary treatment, just as before, the screening or grit removal, sedimentations to remove larger contaminants, larger particles. Secondary treatment, which is the activated sludge, and this is where bacteria can break down components. And then finally, tertiary treatment, which is the disinfection or nutrient removal, solids removal. And below here, you can see how these steps are connected. So the wastewater would come into the treatment plant. You have the screening, preliminary treatment, removing just solids. Primary clarifier, you wait for all the what has coagulated and settled to be collected into primary sludge. The aeration tank, which is where your activated sludge would be. And the secondary clarifier, similar to the first, and then disinfection, and finally it's the final effluent. So it is this effluent now that we are interested in. So after that water that's been used leaves your home, goes to the wastewater treatment plant, leaves the wastewater treatment plant, what happens to it then? Well, this is now considered secondary effluent. So we walked, just to backtrack, we walked through drinking water treatment plants. We walked to what happens when it's sent to the wastewater treatment plant. And now it's considered secondary effluent. And all of this is as background so that we can understand that now when we refer to advanced wastewater treatment, advanced water treatment, this is where membranes would come in. So this is where this technology would be placed. So the secondary effluent is what the membranes would be treating in this potable reuse scheme. So there's a neat kind of distinction here between direct potable reuse and indirect potable reuse that's worth mentioning. Indirect potable reuse means that the secondary effluent that is treated by these membranes goes right back into the environmental buffer before going to a drinking water treatment plant. Direct means that right after it's treated here, it would go directly and skip the environmental buffer. So this is the last treatment train, I promise. So this is what happens at this stage. So now that we've finally placed where membranes are in the whole scheme of conventional water treatment, let's look at what membrane treatment really is. So we're zooming into the reverse osmosis process here. So the secondary effluent that's from that wastewater would come in. It would go through microfiltration, which we'll talk about in a little bit. That's also a type of membrane. It's different from the reverse osmosis membrane in that it's a low pressure membrane, and reverse osmosis is a high pressure membrane. Microfiltration is very often used as a step before the reverse osmosis to catch any particles or to treat that water as much as they can before they send it to reverse osmosis, which is the highest filtration technology. So after these kind of protection steps of the reverse osmosis, here you see the reverse osmosis modules. This is kind of what they look like, these white tubes. And each of these white tubes has a spiral wound RO module within it. So when I say spiral wound, what do I mean? So each of these modules has membranes, and membranes are like flat sheets of paper, but they're spirally wound in these tubes. And the feed water, or the dirty water that needs to be filtered, goes in through the side, and the permeate, or the clean water, would trickle through into the center. So note that after reverse osmosis, you have advanced oxidation and an engineered storage buffer, disinfectant resist, similar to the drinking water. After it's treated, you have the disinfection. And that's now considered advanced water treatment when you go from secondary effluent to supplementing a drinking water supply with what was wastewater before. So many people, when they think of filters, think of one type of operation of that filter. So if you see here, many people think, okay, green here through a membrane, the black, and you have clean water on the other side. And that's not wrong, but that is one of two common methods that these membranes are operated under. And that's called dead-end filtration. Typically, that's used for more lab studies. So if I'm interested in testing a membrane's performance or how much it can reject of a certain compound, let's say caffeine, I wanted to see how much caffeine it can reject. This is the setup that I would be likely using. However, in real full-scale plants, cross-flow filtration and this other setup is often used for treatment of water. So the feed will run parallel to the membrane. Actually, the permeate will come through and the concentrate will continue through. So that is what this is. It runs parallel to the membrane. The feed water comes out here, the dirty water, and the permeate will trickle through. So most real plants, full-scale plants, use cross-flow filtration. So membranes are used for water treatment, obviously. However, they're not bound to just being used for the water treatment industry. They're also used in food and beverage industries. For instance, proteins can be separated in whey for the production of protein concentrate. Membranes can be used for the clarification of apple juice and wine. They're also very critical for the production of ultra-pure processed water streams, such as those that would be used in pharmaceutical industries or microelectronic industries, and also are very important for usage on the International Space Station, which is kind of cool because they treat urine distillate and condensate from the cabin of the space station to reuse water, because obviously shipping water up there would be much more expensive than trying to reuse whatever they can. Concentration of apple and pear juices by nanofiltration at low pressures. So that's another application. So the application that I will be talking about is for the water treatment industry mostly. So there are four main types of membranes. Microfiltration, which recall that that was one of the protection steps for the reverse osmosis treatment step. Microfiltration often can reject suspended particles such as bacteria, dirt, or colloids. And as we go down farther, they become higher and higher and higher in terms of efficacy for what they can reject. Ultrafiltration can reject macromolecules, such as fats and proteins. Nanofiltration can reject sugars and divalent ions, such as sulfates. And then when you get down to reverse osmosis, you've noticed that like only water passes through. That's the ideal. And reverse osmosis membranes can reject monovalent ions such as chloride. So I will be focusing mostly on the high pressure membranes. And the high pressure membranes are the nanofiltration and reverse osmosis membranes. The low pressure membranes are the microfiltration and the ultrafiltration. So nanofiltration and reverse osmosis membranes are effective at removing emerging contaminants such as pharmaceuticals and pesticides and endocrine disruptors in addition to these monovalent salts. And then they can also reject something called disinfection byproducts. So what is a disinfection byproduct? Well, disinfection byproducts are a byproduct of disinfectants or oxidants such as monochloramine or chlorine, which are two really commonly used disinfectants in United States utilities for disinfection. And the disinfection byproducts form when that reacts with natural organic matter, which can be decomposing leaves, for instance. Where's the picture? Let's see. It is a function of time, temperature, and pH, and that's important for their formation. And it's also important to note that the formation, the types and the speciation of what forms is a function of the matrix that it's in. So disinfection byproducts are often regulated, and they are regulated in the United States by the EPA, and they're regulated in two groups. One of the groups is trihalomethanes, and that's the four that you have listed here. Bromodichloromethane, bromoform, dibromochloromethane, and chloroform. And there are health effects associated with some of these if they are in your drinking water. For instance, liver, kidney, central nervous system problems, etc. The second group that the EPA regulates is called the haloacetic acids. These are the dichloroacetic acid, trichloroacetic acid, chloroacetic acid, bromoacetic acid, and dibromoacetic acid. These group of 5 chemicals are in aggregate regulated, which means they're not regulated one at a time. They have a limit that in some they have to be less than. These are also associated with various types of cancer if in over a long period of time it exceeds the maximum contaminant level. So what is the maximum contaminant level and what is the maximum MCLGs, maximum contaminant level goals, and they're non-enforceable health goals. They're based solely on possible health risks and exposure over time, and they take into account a margin of safety. Based on these MCLGs, the EPA then gives us a recommendation for the MCLs, maximum contaminant levels. These are enforceable regulations, and they take into account cost, benefits, and the ability of the water system to detect and remove these contaminants. So these are more tangible targets for utilities. So for the THMs, so recall that there were two groups that were regulated, the trihalomethanes and the haloacetic acids. For the trihalomethanes, the total THMs for regulation has to be below 80 ppb, and that's for all four of those listed there. For the HAAs, it's a little bit lower at 60 ppb, and again, that's for all five of the haloacetic acids. And there are over 600 types of DBPs that have been identified in chlorinated tap water. Anytime you chlorinate water for drinking water purposes, you will have disinfection byproducts present, most likely. So what does all this disinfection have to do with membranes? Why are DBPs even relevant to membranes? So remember when I said one of the challenges that membranes face is fouling. There are many types of fouling, but one of the main ones that I will focus on is called biofouling. Biofouling is caused by it's a microbial accumulation on the membrane surface, and when this happens, there's a significant reduction in permeate flux. You need higher operation for these membranes to clean water. Again, these are high pressure membranes, so when there's a coating on them, you need more pressure to push the water through. And you have impacted rejection and water quality. So on the right side there, you see what a clean membrane looks like. This is not the spiral wound element, but this is what would be spiral wound inside. Excuse me. And then you have the biofouled membrane underneath. So what do we do to avoid this issue and maintain the integrity of membranes? So one solution, the most common solution, is disinfection prior to the membrane with either chlorine or chloramine. So that's the kind of bridge between, so the disinfection byproducts that I was talking about earlier, that's the bridge for why that would be relevant. So if you are disinfecting prior to a membrane, disinfectants can damage that polyamide layer, that top very thin layer of the membrane. And it's important to make sure that the chlorine is dechlorinated, or there is a step to make sure that the residual is less than 0.1 milligrams per liter, so that there is not damage to the chemical structure that is the polyamide layer. So after the water passes through the membrane, then you will likely have another chlorination event for the residual. So to review a little bit, these are pressure-driven processes, and there's semi-permeable membranes. You can think of them as fancy filters, and the mechanism by which they remove compounds is size exclusion, just like a regular filter would be. Charge, so positively, negatively charged compounds, and hydrophilicity or hydrophobicity, so the kind of likelihood that that compound would prefer to stay in the water phase or prefer not to stay in the water. So you have your feed water, which would be your dirty water. You send it through, again, the nanofiltration or reverse osmosis membrane, and then you have your permeate, which is another word for the clean water, and your concentrate. Here you have an image of what just to get an idea of the thickness of the polyamide layer with respect to some of these polysulfone and polyester layers, and the density that's associated with those. So, excuse me. The nanofiltration or reverse osmosis membrane structures typically have three layers. They have an active layer, which is about 20 to 200 nanometers in thickness. They have a polysulfone layer, which is between 20 and 50 micrometers. Sorry, I have a cold. 20 to 50 micrometers in thickness, and the polyester layer is between 50 and 150 micrometers in thickness. So the aqueous feed, or the dirty water, would come in contact with the active layer and permeate that way. So in terms of preparing, so we're going to go back a slide here. In terms of preparing that top yellow layer, the active layer, that's the layer that's kind of the main contaminant rejection. That's the layer that is most responsible for cleaning your water. So there are two common active layer synthesis procedures to make this top layer, and one of them is fully aromatic, and one of them is semi-aromatic. And the difference there just means really both of them use this trimethyl chloride monomer here, but what it's reacted with is a little different. So here in the fully aromatic polyamide structure, you react it with something called M-phenylenediamine, MPD. And on the other one, semi-aromatic polyamide structure, you react it with something called piperazine. When these two respective reactions occur, they produce this polyamide here, and then the semi-aromatic reaction produces a polypiperazinamide that you see here. So not to get kind of bogged down in the chemical structures, but this is the actual structure of the active layer, that yellow top layer of the membrane. So for reverse osmosis membranes, they're typically fully aromatic structures such as this. So it would be this structure. And for the nanofiltration membranes, those can be either semi-aromatic or fully aromatic. So in a recent study, there was evidence that there's some kind of precursor leaching from nanofiltration membranes. So this study looked at 5 various types of nanofiltration membranes, and they measured using something called formation potential. They measured what is leaching from these compounds. So they basically, and you can see the visual here, they put distilled deionized water through, so laboratory grade water, ultra pure water through the membrane. And they then take samples of the permeate, so the other side of the membrane, to see if there's something coming off of the membrane itself. But because you don't know what you're looking for, that's typically pretty difficult. So they use something called a formation potential test, which means you take the sample post-membrane treatment and you react it with a disinfectant. What they used was chloramine. So why react with a disinfectant, and why does that help you see if you don't know what you're looking for anyway? So what this helps you do is that the disinfectant will likely, if something is there, react similar to how the disinfection byproducts formed when natural organic matter reacts with disinfectants. This chlorine, or chloramine in this case, reacts with whatever is coming off of that membrane, and then we have methods to measure that. This paper in particular measured NDMA. It's N-nitrosodimethylamine, which is just another one of those GBPs that I mentioned. And they found measurable levels of these leachates coming from the membrane. So the question here is, like, now they know something is leaching from these membranes that are used very widely, but they don't know what it is, because these methods are formation potential methods, and they're not able to tell you the identification of the precursor. They're just saying, if we react X unknown with chloramine, what will we be able to measure? They measured NDMA. So there are gaps in knowledge here in that membrane leachates and their reaction products with chlorine disinfectants might not be amenable to identification by existing disinfection byproduct analytical methods, which basically means we currently have suggestions of evidence that there's something coming off of these membranes, but the methods that we have in place right now look for targeted compounds, and we need something that'll be able to tell us what's coming off of these membranes. And once we identify what that is, how is that then impacted by chlorine, and what subsequent byproducts can we get from that? Because if the membrane is contributing compounds to the water that are then being disinfected, it's really important to understand the leachate as well as the byproducts that might come from that. So the first objective we had was to develop methods to detect some of these leachates from nanofiltration membranes. So when I say develop methods, that's everything from the concentration procedure. We use both liquid and solid phase methods, which is something I'll get into a little bit later. Chromatography, liquid and gas chromatography was used in these studies. And these are just like analytical tools that we've coupled together to give us the most precise, most clear understanding of what we see in this unknown matrix. The detection we used ultraviolet detection. We used an electron capture detector. Electron capture detector is one of my favorites. It helps you see low molecular weight, GC, ECD, lets you see low molecular weight compounds that contain an electronegative atom. And mass spec. We also use mass spec. However, using conventional LCMS or liquid chromatography mass spectrometry is quite challenging when you don't know quite what you're looking for. That's why we use something called derivatization, and I'll get into all of this a little bit later. So the membrane that we selected to begin with is an NF90 membrane, and they are, just to kind of remind you, the fully aromatic structure, trimethyl chloride reaction with 1,3-benzene diamine, or also known as MPD. That's the structure of the membrane that we use for these studies. Molecular weight cutoff means anything that's above a molecular weight of 100 to about 200 is typically rejected. That's how tight the filter is. The NaCl rejection or salt rejection, sodium chloride rejection, is greater than 97%. And the free chlorine tolerance, remembering that these membranes are sensitive to chlorine, is less than 1.1 ppm. Challenge, because now you're trying to concentrate things that you don't know what they are. So typically, when you're using solid phase extraction, or SPE, you would pick a solid phase cartridge. So these are these cartridges right here, this tiny little bit of solid phase. Your sample is run through these cartridges, and these little solid phase areas here will retain the analyte in your sample. And then afterwards, when your sample has passed through, you take a solvent of another kind to elute that and release those into your sample tube. Typically, when you're selecting SPE cartridges, you would go with properties that are consistent with things that you're looking for. So for instance, if I have a cation that I'm targeting, then I would probably get a solid phase that's a strong cation exchange resin so that I can capture cations. Unfortunately, because we don't know what it is that we're looking for, we had to take a little bit step back and use a more broad screen approach. So what we used is the Oasis HLB cartridge. Means is LB, hydrophilic lipophilic balanced copolymer. So what this means is that it's ideal for a broad screen analysis because it will retain a broad screen of analytes. So hydrophilic meaning water loving, lipophilic water hating. Instead of zooming into a particular characteristic. So HLBs are a broad screen, general first-hand approach. For future reference, though, if you're looking for SPE that would fit your matrix, you would look at whether your matrix is aqueous or organic. You would look if you're interested in strong cations, weak cations, polar, nonpolar compounds, and then kind of use this diagram to help select which type of solid phase that you need. But again, since we didn't know, we went with HLB. So a little bit about our methods. We took a membrane coupon and we just reacted it in a static cell or a static bottle, sample bottle with lab grade water. We kept it on a shaker for 4 hours. And we left it there for 7 days at room temperature to see if anything comes off of those membranes and if we can capture it in that lab grade water. Then we'll run it through that Oasis HLB, the SPE that I was mentioning earlier, the kind of broad screen capture, and hope that our analytes are captured in and retained on this cartridge. Then we eluted that with acetonitrile, and in hopes of further concentrating, so my sample went from 100 mils right now to 3 mils. In hopes of further concentrating that, we can use something called a blowdown, which will evaporate extra solvent and hopefully retain your analytes in the sample. So then we blowed that down to dryness, our 3 mils at that point. We blew it until the sample was gone. And then we reconstituted that in 500 microliters of acetonitrile, which we then analyzed. And you'll notice here in red that some samples were derivatized. So that's something we'll talk about in the next slide, but derivatization is useful for tagging compounds. So this was in blue is our generalized approach for looking at membrane leachates. And here in red, we decided to derivatize a subset of those. We'll react with pentafluorobenzoyl chloride, which is our derivatizing agent. And then that we can look for as a tag. So if you look here, polyamide layer, top layer of the membrane, we have those two monomers that reacted, that created this fully aromatic structure. And now we're reacting it with pentafluorobenzoyl chloride to hopefully tag some of these functional groups. So if something is coming off, pentafluorobenzoyl chloride can react with amines and amides, for instance, and here's an amine. It can react with those functional groups, tag it, and then you have a way to search for these fluorinated groups if they're there. So what we saw was kind of interesting. We saw that here's a control sample that had no membranes, and that was just the laboratory grade water on the shaker, no membranes. Here we saw that there were several peaks of leachate when we added the membrane in, extracted the membrane, concentrated the sample. And we see that we do have 2 peaks not present in the background sample, which means, based on UV data, that something's coming off of these membranes and we don't quite know what that is. So LC-UV can tell you if there's something that is able to absorb at a particular wavelength. So right now we were monitoring at 270 nanometers. And basically all that means is if it absorbs at light at a particular wavelength, it'll be able to tell us. What it's not able to tell you is structure. So this is not a mass spec. It can just tell you how much of a compound that has a chromophore is there. A chromophore just means ability to absorb light at a particular wavelength. So then when we derivatize that sample with the pentafluorobenzoyl chloride, you'll notice that there is a new peak that emerges at, well, there's 2 new peaks. There's one here, which is the excess pentafluorobenzoyl chloride. That's what we added, so we're not interested in that peak. But there's a peak right here. And this peak at 12 minutes suggests that whatever was coming off of the membranes is now tagged. So we use something called a QTOF-MS. It's called the quadruple time of flight mass spectrometry, and it combines high performance time of flight analysis with mass spectrometry. So what this means, why it was appealing to me, is because it has high sensitivity and high mass accuracy. So if I'm looking for structural confirmation, this is a really useful instrument to have. So when we ran those same samples on a mass spec, the same samples that we saw, okay, now there's something coming off of the membrane, we see it on this instrument that can't tell us the structure, but we still have those samples. Now we can run those samples on a mass spec, and we can go peak by peak and figure out what the structures of those are. So here, you'll notice that happens to be the identification for M-phenylene diamine, which was one of the monomers used in the synthesis of membranes. So that was interesting to see that, okay, one of these excess monomers is coming off. So there are subsequent questions, right? How long is it coming off? How do we clean this off the membrane? So we kept going. Here, again, the structure of the derivatized MPD. So Previously, the mass spec told us, okay, MPD is leaching. This is one of the compounds used to make the membrane, so that was expected. And then MPD is able to react with the pentafluorobenzoyl chloride, and we have a tag, and now I can see that has reacted. So since MPD is leaching from the nanofiltration membrane, there are some subsequent questions that come up. Like I said, how long is MPD a residual leachate? And also, how are these leachates, going into objective 2 now, how are these leachates impacted by chlorine? So solid phase extraction is not the only way that we can concentrate samples. And to be able to look at some of the byproducts of a reaction between MPD and chlorine, or to see how chlorine impacts MPD, we need a different kind of concentration mechanism. So solid phase extraction, which is what we talked about earlier, is fantastic for non-volatile compounds, so compounds that won't be lost into the atmosphere. Liquid extraction, however, LLE, is useful when you're working with compounds that are volatile, and justifiably so. They will then be analyzed on a gas chromatographer, so it'll be using that volatility to help separate those compounds and analyze them. So what is liquid extraction? So liquid extraction means that you have your sample. Here it's the aqueous phase with the little green dots. That can be my water sample, and the green dots are indicative of the analytes that I'm looking for, these unknown byproducts when I chlorinated things that are coming off of the membrane. Don't know what they are, but something's coming off of the membrane, and I reacted it with chlorine, just like the paper that we talked about did. And now I'm interested in extracting those, concentrating those, and analyzing them to figure out what they are. So I do that by adding an organic phase, which can be MTBE or hexane, for instance. And they're not miscible. So you'll have 2 layers, and after shaking, you can get your organics to extract from the aqueous phase into the organic phase. So I can use this now to run on my GC instrument. So interestingly, when we use the GC ECD, we saw, so again, GC meaning I'm looking for volatiles, and ECD meaning I'm looking for volatiles that can be detected by the characteristic of them having an electronegative component. So what we did here was then I put membranes into the sample bottle, let that leach for X amount of days, I think it was 5 days, take the membrane out and chlorinate whatever has come off of that membrane. And what we found was that, in fact, there are several byproducts that come from the chlorination of what is coming off of these membranes. So you see that one of the peaks is around 7.2 minutes, and we ran up top is a sample, same method of the sample of THMs, trihalomethane. So they react on the instrument, and do they align with any of these unknowns that came from our sample? And at 7.2, there was a match for chloroform, which is one of the regulated THMs, trihalomethanes. There are several other byproducts here that have not been identified yet, and we're working on those right now, but an ECD is not able to tell us, similar to how the UV is not able to tell us structure. We need to take this sample on a GCMS so that we can speak to the structures, the mass spectra of some of these, but we're in the process of others. So future directions, we can assess whether nanofiltration membrane leachates or their reaction products with disinfectants, so the MPD that was coming off, or some of these chloroform and low molecular weight compounds that we see here. The next step would be, are they able to permeate, right? Because right now our tests are in these solid, are in these static systems, and I'm not actually pushing the water through the membrane. So are these leachates and byproducts able to permeate the membranes? And recently studies have shown that yes, they're able to permeate through the membrane and be in the clean water side, which is critical. If so, and they are, the next step would be to design a procedure that would ensure that these membrane leachates have been removed prior to membrane usage. So typically what's used are acid-base rinses or very low dose chlorine washes. And just making sure that those are suitable for removing some of these leachates coming off of the membrane. And of course, another target would be to broaden the range of membranes studied. So right now we only looked at a nanofiltration membrane, and we only looked at one type of nanofiltration membrane, and that was NF90. So it would be interesting to see what kind of byproducts can be detected from various nanofiltration, reverse osmosis, semi-aromatic, fully aromatic type of membranes. So one of the interesting, kind of to pivot from my research a little bit, one of the interesting directions that some groups in our department are focusing on is the incorporation of these nanoparticles into the active layer. And what these nanoparticles do, or it's a change in the way that you synthesize the membrane. But what these can do is change the performance of your membrane. It can inhibit, for instance, biofouling. So one of the papers here in 2014 is the incorporation of titanium oxide into the active layer. So here we see, just to recall the structure of a membrane, the active layer is that top layer. So what these papers are really doing is embedding nanoparticles within that top layer and then assessing how that impacts rejection. Interestingly, you see another here, incorporating nanoparticles into thin film reverse osmosis membranes for anti-biofouling properties. So these nanoparticles are able to, for instance, contribute to to reducing biofouling, reducing the amount of microbial accumulation on the membrane. So not only changing membrane properties in terms of what they can reject, but also changing membrane properties in terms of how susceptible are they to some of these problems like fouling. And another really neat thing I would like to mention is this other paper. Again, not necessarily related to my research anymore with the membrane leachates, but a really neat avenue to producing membranes is 3D printing polyamide membranes for desalination. So this paper actually found that reverse osmosis membranes, instead of producing them the way that they're produced now with the polymerization reaction, they can actually use 3D printers to produce these membranes, and at optimum conditions, the membranes appear to be better at desalination than commercial reverse osmosis membranes. So I thought that was kind of neat in terms of like innovation and using new technologies to improve a treatment technology. So that is the conclusion of my talk for now. And if you guys have any questions, I'd be more than happy to take them about my research, about graduate school, being a student, UNC Chapel Hill, anything. I will do my best to answer those.
So Alma, while you were having like the first part of your presentation, we got questions from Ali from Tuzla. Actually, a lot of questions, so if you are ready, you can start answering them. First of all, thank you for the great presentation, and it was like pretty much interesting, even for me, who am IT expert. So, it's Ali Mokais. He's sending you greetings from Tuzla, and he has a few more general questions. So, there are many water contaminations on macroscopic and microscopic levels. ALS, one of the most talked about recently, is plastics and microplastics. So how do you see engineers of the future best addressing the issue? And besides them, what else can be done to tackle this colossal issue?
So for microplastics in particular, I don't think that membrane technologies would be kind of the first channel or the first kind of barrier there. Particularly, I do not work with microplastics, so I'm going out on a limb here, but I'm pretty sure that microplastics themselves would accumulate on that membrane. But for instance, if a membrane can reject monovalent ions, then they would be able to likely reject some of these microplastics, right?
Okay.
But this would be a very, very expensive application of the technology. I think you'd be stuck with like fouling of the membrane surface, and you'd end up having to clean these membranes. And every time you have to clean these membranes, they use like chlorine washes or acid-base washes. Every time you do that, these membranes are more and more damaged in that process. So in terms of a solution for microplastics in like the grand scheme of things, I don't think I have that answer, but I don't know that membranes would be helpful, but perhaps not the first barrier.
Okay. So the next question is, actually you partially answered it, but however, a lot of articles and researchers are focused on detecting microplastics in water. He would like to have more insight on how this is not only being detected but removed, and also do you have any insight on resources that you can provide on that topic?
Can you repeat the second part of that? I didn't quite hear the second part of the question.
He would like to have more insight on how it's not only being detected but removed, and also do you have any insight on resources that you can provide on that topic?
In terms of research and insights, there are definitely I can forward you a couple of papers that might be of interest to you, but I don't, in terms of detection of microplastics, I can see how detection of byproducts from those or degradation materials of those byproducts might be, of those microplastics might be able to be targeted, but microplastics themselves are difficult to analyze. It's still in solid form, so those might be a little bit difficult to, unless you can digest those, or unless you can kind of what I'm doing here. I'm not necessarily detecting pieces of the membrane, but I am detecting byproducts from the membrane. So if those microplastics are contributing to or degrading into some kind of chemical structure that you can target, then that might be a method for detection.
Okay, so the last question from Ali is also about microplastics. He found the
I'm going to learn all about microplastics.
Yeah, he just loves microplastic, it seems to. So he found an article which, according to a new assessment by World Health Organization, is saying that microplastics are increasingly found in drinking water, but that there is no evidence so far that it poses risk to humans. He wants to know, what are your thoughts on this?
So I heard that I read an article a couple months ago, and it was kind of tracking the impact of microplastics on fish, on animals. So there's evidence that it's harming kind of their breathing pathways, for instance, but for I don't know if we have enough information to confidently say that it's not impacting human health. Just to tie it back to what I've been doing, some of these, for instance, the disinfection byproducts, they're ubiquitous within drinking waters that are chlorinated, and yet to be able to speak to toxicity studies or health risks of humans, that is particularly difficult when you're looking at, for instance, mouse models, or you need some kind of assay, and then you have to extract that assay to see how that would be relevant to humans. And in addition to that, another complexity to that is just the time, the duration of exposure, right? So to be able to say confidently that microplastics have no impact on humans, I think that is going too far, because you need studies that are much longer. You need to be able to track these exposures and health endpoints. And that's really difficult when you're looking essentially at what is like an epidemiological study, right? When you have confounding variables of, it's not a closed system, like humans are not a closed system. So that would be, my thoughts on that are just, we obviously need more data collection there, but also that is a very difficult problem to pinpoint whether microplastics themselves have an endpoint unless you have, every assay has its limitations. Every experimental design has its limitations. So those are kind of my first thoughts.
Okay, that's all from Ali. He thanks you. The next question, actually two questions, is from Ivana Trulich. She wants to know, does the mass use of desalinated water have or will have effect on sea ecosystems? And what's your opinion about this?
Are you asking about the waste from the membranes, how that's disposed of and how that would be impacting?
I think that she believes that usage of seawater and desalination of that water, how it will affect to the ecosystems. Even I just write if that's okay with your question.
Yeah, so I'll start answering, and then obviously if I missed something, let me know. But that's a really, really good question. One of the main, I didn't address it in this talk, but one of the main concerns with membranes is, one, it's a high pressure system that uses a lot of energy to produce. But when you don't have an option, or when you are lacking in your access to water sources, additional water sources, energy becomes, the high energy cost becomes something that you're still willing to consider. However, the second really big concern with membrane operation is this production of, actually, if I can find, do you guys still see my slides by chance?
Yeah, they see.
Great. So I'm trying to find one of my slides on the spiral wound. So if you recall this slide, cross-flow filtration is typically the common way of operating these membranes in full-scale treatments. So what this means is that, yeah, you have a permeate flow, and that's typically about, depends on the plant, of course, but about 70% recovery of the water that goes in. About 70% of that, give or take, would be recovered into clean water. But that means that the rest of that is brine now, or very, very salty water, and it's because it's rejecting sodium chloride. It's called the concentrate because it's concentrating up the sodium chloride. And then what do you do with that? So actually, there have been several conferences, and that's a really insightful question, because several conferences that I've gone to have focused on just that. How do you eliminate or dispose of a brine now? Because can you put it back into the ecosystem, and you're increasing the salinity of that ecosystem. To what end, right? To what degree? That I probably couldn't answer, because you're right. The ocean is vast. How much are we actually changing the salinity of the ocean? Cannot say. However, I could say that probably local, where those discharge points are, undoubtedly there are some impacts that are going to be present because of the change in salinity. Right now, there are technologies called zero liquid discharge, ZLD. Those projects are trying to figure out how they can make sure that there is no liquid discharge, that you have a solid endpoint, that when you finish with your membrane treatment, that you have solid salt. And so that's another possibility for reducing ecosystem impacts, I think.
Okay. So the next, first thank you for answering. There's one more question from Ivana. She's asking, are good minerals, magnesium, kalium, also removed during reverse osmosis? And how do you mineralize water after the treatment?
Yeah, so monovalent and divalent ions are rejected by reverse osmosis. So for instance, chloride, when I say valent, that just means the charge. So if the charge is more than one, so chloride is a -1, if that charge for magnesium is higher, then yeah, it would be rejected by these membranes. And I'm just trying to find this actually. Okay. So you can see that divalent ions begin to be rejected at the nanofiltration level. Monovalent ions, you would need something a little bit more tight, like reverse osmosis. Calcium sulfates there.
Okay. Since we don't have any more written questions, I will leave space for the people to write more questions. So if you have questions, please write them. While we were waiting, I have one question. So I come from a city called Tuzla, which is a city that from, I don't know, age of the time since the city was founded, had a problems with water. And constantly there were reductions and everything up till to the last few years when they built a dam. So right now we are having water. But during your presentation, I was struck because Tuzla has like old Pannonian Sea beneath it. So
Tuzla has what?
Sea. City has beneath the sea. So I'm interested. Do you believe that with membrane and desalination process, Tuzla could have a sustainable water source?
Yeah, well, like technology-wise, I mean, anywhere you have seawater, you can use membranes to desalinate. But the balance there is that it's a very expensive alternative. So I mean, it comes down to, this technology is available and out there, but it's an investment, like the capital cost just to build the plant, and then the costs for membrane upkeep, like these modules are really, really expensive. So would the technology work in a different part of the world for also the same purpose of desalinating water? Yeah. Would I recommend membranes to every single place that has access to the sea? I don't think so, because there are other, or it depends with what your starting matrix is. It depends what the water quality there is, and it depends what the regulations there are and what you're trying to meet. So I wouldn't necessarily go as far as to say, membranes are like this catch-all, because they do have their downsides, and we kind of touched on those. So I wouldn't, but technology as is would work, but it depends on your goals, it depends on the regulations, and it depends on the cost.
Okay. And the last question from me is, we live in Bosnia-Herzegovina. I think that neither one of the place in our country does have wastewater facility treatment. What do you recommend that every single of us can do to somehow recycle the water, to save the water, and to be part of the 6th SDG?
That's a good question. So again, I think it depends on, are you asking about the water quality itself and my recommendations for just ensuring that the water quality is sufficient, or what is the?
So I'm asking what every single individual can do to recycle the water that they have, to do some kind of waste management system of its water inside of its house.
Well, there are obviously like catchment. You can catch rainwater and reuse it that way, or you can just conservation is the easy answer, right? But I don't know that it's very easy here to, for instance, if I had a question about the water quality, or if I had a question about whether reuse was meeting drinking water quality requirements, it's very easy just to go to the local utility, provide a report with parameters that have to be met for regulation and how they meet that. So perhaps you can let me know how that is in Bosnia. Do you have access to the same types of, if you were curious about the water qualities? I think many people are on like well water, right?
Yeah.
So that's a little bit different. So well water itself can be intruded by like groundwater contaminants. If you have companies that are dumping contaminants that can infiltrate into that groundwater reservoir for private wells, that becomes a little bit more difficult in terms of like recommendations for making sure that water is safe to drink and how to. But conservation is the easy answer. But in terms of quality, that's a little bit more difficult, particularly when people are on private wells. When you don't have that, request a report and let me see what's in my water. There's definitely a lack of regulation even here for private well water quality.
Okay, so thank you for answering my two questions. So while we were waiting, and while you were actually answering my last question, you somehow touched the next question by Amir Muratovic, and he's asking you, is this statement true? So in Bosnia and Herzegovina, we constantly hear among people that we have a lot of fresh drinkable water. On the other side, we constantly see industrial waste disposed in our rivers, lakes. To which degree?
So are you asking, is it true or false? Well, it depends. I guess it depends where you are. It depends on like the geographic location of these like discharge points from the companies. It depends what they're discharging. Can it be removed? Is it like biodegradable? Is it photosynthetic? Does it degrade when the sun hits it, for instance, so that by the time it gets to you, it's no longer, I wouldn't say no longer dangerous, but less impactful. So I think it depends on a lot of, that's not quite a true or false. It would be very site specific, I think. And I would definitely need more information about the particular site to be able to say. And when you say safe can mean a lot of things. Safe can mean microbiologically safe. Safe can mean safe for now, but for instance, with the disinfection byproducts, exposure to X chemical for 25 years and it's not safe anymore. So I think there has to be a little bit more, definitely not a true or false, yeah.
Okay, so I somehow got this question wrong. So he was, actually you answered it. So his question was, to which degree is this statement true? So you answered, however, the question. So from now on, we don't have any more questions. I would like to thank you for being such a great presentator. I think that world is going crazy for Greta Thunberg, but we in Bosnia should be so proud of you for being such a dedicated environmental scientist, and because you want to create this world a much better place. Thank you.
Thank you so much for the kind words. I really appreciate it. And it was really, really an honor to speak with you guys. And honestly, if you have any other questions, and they don't necessarily have to be related to my research, if you have any questions for graduate school, anything, I'd be more than happy to talk with you about those. But yeah, it was an honor to, I wish I could actually see some of you. That would be kind of cool. But definitely an honor to speak to you, and thank you for your questions. I hope I answered them.
Okay.
And if I didn't, let me know. I can follow up.
Okay, thank you so much again. By this, we're ending our webinar. Thank you again, and hope to see you soon and hear again.